Chapter 5, Section 5.1, Angles and Radian Measure. The objectives in this section include defining and discussing angles, different types of angles, the degree and radian measure of angles, specifically converting between degrees and radians and vice versa. We'll learn how to draw angles in standard position. We'll define coterminal angles, which means angles that share the same ending point. We'll find the length of a circular arc, and we'll use linear and angular speed to describe motion on a circular path. Let's get to some of the preliminary angles. An angle is formed by two rays that have a common endpoint. So here's our common endpoint here, which is called the vertex. We use the one side to be initial and the other side to be the terminal. And we fix the initial side and we rotate the terminal side like that, and that rotation forms the angle. An angle is considered to be in standard position if its vertex is at the origin, so you want to draw your angle on the Cartesian coordinate system, initial side always on the positive x-axis, always on the positive x-axis, and then you want to rotate the terminal side of the angle like this. Angles that are rotated counterclockwise are considered positive rotations, and angles that are rotated with the clock clockwise are considered negative rotations. Positive rotation, yes, it's against the clock, but we label the quadrants against the clock as well. Quadrant 1, quadrant 2, 3, and 4. So in this direction defines a positive rotation. So here's a description that I mentioned just a moment ago. Positive angles are rotated in this direction from right to left, and this way clockwise with the clock are considered to be negative rotations. Special type of angle is called a quadrantal angle. A quadrantal angle occurs when you lay the initial and terminal side on the positive x-axis and you rotate the terminal side. If you rotate it 90 degrees like this, that would be a quadrantal angle. If you rotate it a half rotation like this, 180 degrees, or if you keep rotating to a 3/4 turn, 270 degrees, or continue rotating all the way back to the positive x-axis, those are considered to be quadrantal angles. There are two measurement systems that we use for angles. One is common, degrees, and the other one, perhaps not so common, is radians. Since there are 360 degrees in a circle, we can subdivide that in its quadrants, its quadrantal angles. So a 90-degree angle is called a right angle. Acute angles measure less than 90. Right angle is exactly 90. Obtuse angle is between 90 and 180, so that would be rotating from the positive x-axis not quite as far as a half rotation. An exact half rotation would be a full 180 degrees, and that's called a straight angle, and angles that are between 90 and 180 are called obtuse. In calculus and more advanced math, degrees are rarely used. Radian measure is the sole way we measure angles, and this is because the formulas that are generated in calculus are more simplified when you use the radian measurement system. An angle whose vertex is at the center of the circle is called a central angle. The radian measure of any central angle of a circle is the length of that intercepted arc divided by the circle's radius. So in other words, we use a formula, S equals R theta, where S is the arc length, R is the radius of the circle, and theta is the central angle. So as described here, the central angle is the length of the intercepted arc divided by the circle's radius. So in other words, theta then, solving this equation, is equal to S over R. And that is the description here being mentioned. Let's take a look at the definition of a radian. 1 radian is the measure of the central angle of a circle that intercepts an arc equal in length to the radius of the circle. So if you look carefully at the picture, we have the radius of the circle here being R, and the arc length here, typically denoted by S in the equation, is also given by R, so the arc length and the radius measure the same. When that occurs, then this central angle is defined to be 1 radian. So, for example, what happens if this arc length here were twice the distance of the radius of the circle? Then that would measure 2 radians. And if this were 3 times the distance of the radius, then that would measure 3 radians, and so on. Here's the formula that I mentioned just a moment ago. The measure of the central angle theta that intersects the arc theta equals S over R. Okay, also note that when the radius of the circle is 1, the measure of the central angle is equal to the arc length. And that's another way to define radian measure. Take a look at an example. Central angle theta in a circle of radius 12 feet, so R is 12, intersects an arc length of 42 feet. Okay, that's the distance traveled along the circle then, 42 feet. What is the radian measure of the angle? Well, since theta equals S divided by R, the arc length is 42 feet, the radius is 12 feet, 42 divided by 12 is 3.5. Notice that the units divide out, and the measure of the central angle is in what we say radians, the 3.5 radians. We can convert between degrees and radians and degrees. It says here, basic relationship pi radians equals 180 degrees. Well, distance around a circle is 360 degrees, and that's in the degree measurement system. But circumference of a circle is 2 pi r, and if the radius is 1, then the circumference is 2 pi. So that means that 360 degrees is equal to 2 pi radians. And if we take this as an equation, dividing both sides by 2 gives us 180 degrees equal pi radians. We say rads for radians. And that's where this relationship here is coming from. So to convert from degrees to radians, multiply the given degree by pi over 180. Then the degrees here, the multiplier, and the degrees here in the denominator will be eliminated, and you'll end up in the units of radians. And conversely, the reciprocal of this, 180 over pi, will convert from radians to degrees. Incidentally, if we take a look one more time right here, look at this equivalency right here. If you divide both sides by 180, then 1 will equal pi over 180 rads. So this tells you how big one degree would be. Or you could take this equation and divide both sides by pi, so 180 degrees over pi would be equal to 1 radian. So it tells you how big 1 radian is in degrees. Okay, let's take a look at a conversion example. Example 2. Convert each angle in degrees to radians. 60 degrees. Okay, by the conversion factor, multiply 60 by pi over 180 and then reduce the fraction 60 over 180 to be 6 over 18 or 1/3. So 1/3 pi, or we say pi over 3 radians. A different way to think about that is pi, if the circumference is 2 pi, pi is a half rotation, which is 180 degrees. So you can think of this as 180 divided by 3, which is 60, or 60 times 3 is 180, so 1/3 of that would be its radian measure. 270 degrees, you can use the conversion factor, multiply 270 by pi over 180, reduce that fraction to get 3 pi over 2, or you could think of 3 pi over 2, let's see. We start here, we end here, that's 90 degrees, or pi over 2 radians. If we have 3 pi over 2, then we can think of this as 3 times pi over 2. So 3 of those 90-degree angles, 1, 2, 3, would put you here at 270 degrees. So 270 degrees would be 3/2, or 1.5 pi. Negative 300 degrees. Well, we can convert negative angles as well by using the same conversion factor, multiply by pi over 180, and simply reduce the fraction 300 over 180 to give you 5/3 pi. So you can think of 5/3 pi as 5/3 is 1 2/3 pi. It's 1 2/3 times 180, and that would be 300. Now this is a negative angle, so we're measuring things this way clockwise, but the formula holds for positive or negative angle measure. Okay. Drawing angles in standard position. Okay. So this helps to explain a little bit one of the calculations I made here earlier. Why is it that here I wrote 90 degrees or pi over 2? So part of what's being illustrated right here is that here's a 90 degree or right angle being made. That represents a 1/4 turn, but it represents a 1/4 turn of the entire distance around. So 1/4 of 2 pi is the same thing as 2 pi over 4, which is pi over 2. Okay. And a half turn, in this picture here, half of the entire distance around, which is 2 pi, half of 2 pi is pi. So that's a pi radian rotation. This is a 3/4 turn. Why is this not 3 pi over 4? Because it's 3/4 of 2 pi, which makes it 3 pi over 2. Or 3 pi over 2 is 3 90-degree turns. 1, 2, 3. And this represents an entire full rotation, or a rotation of 2 pi. Okay. You can also think of rotations as fractional rotations about the circle. Here's an example. Draw and label the angle in standard position, theta equals negative pi over 4. Okay, it's a negative angle, so we're going to rotate in this direction. Always start out with the initial and terminal sides on the positive x-axis. Rotate this way with the clock since the angle is negative. And how big would that angle be? Well, one way to look at it is this is 180 divided by 4. So you could reduce that to be 45 degrees. So in other words, it's exactly halfway into this quadrant. This would be 45 and this would be 45 degrees. Or a different way to think about it is, Pi over 4 is an eighth of a rotation. An eighth of 2 pi is pi over 4. So it's an eighth of a rotation in the negative direction. We say an eighth because 8 of these would make a full rotation. So you can think of that as a fractional turn. It's 1/8 of a full rotation, or 1/8 of 360, if you wish to think about it in degrees. Okay. This is more of an overview of taking the circle in both positive rotations and negative rotations and seeing various common used angles in their degree and radian representation. So 30 degrees being pi over 6. Now you can think of this as 180 divided by 6 is 30. Pi over 4 is 180 divided by 4 is 45. Pi over 3 is 180 divided by 3, or 60. And we have various quadrants here represented, as well as going around in the negative direction. One useful way to think about this is to convert all of these into the same common denominator, and that way you can see fractional bits of rotations around the entire circle, and you can see a nice pattern with the denominators all being the same. So here's a different view of fractional rotations about the circle: twelfths and eighths, sixths, quarters, thirds. So if you're in the radian mode, you take that fraction of 2 pi, and that will be its radian measure. Or if you're in degree mode, take that fraction of rotation about the circle of the total, which is in degrees, 360, and you'll have its degree measure. So in other words, 30 degrees is the same as pi over 6. 45 is the same as pi over 4. By saying that this is a sixth of a rotation means that there are 6 of these in the entire circle. So 6 times pi over 3 would be 2 pi, which is a full rotation. Or if we divide this into quarters, being pi over 2, 4 of those rotations, 4 times pi over 2 would be 2 pi. Or 12 times pi over 6 would be 2 pi. So we're dividing the circle the same way you divide a pizza into proportional sizes. And this is a continuation of that, where we look at halves and 2/3 and 3/4 and 7/8. Again, it's sometimes better to view all of this as the same denominator and get all of these with the same denominator, and you see nice patterns that occur, and they're a little bit easier to count. They're also easier to remember, and you can always reduce that later. Okay, let's take a look at something called coterminal angles. Co means sharing the same. Terminal means the terminal side of the angle. So these are angles that share the same ending point. Two angles with the same initial and terminal sides, but possibly different rotations, are called coterminal angles. So in other words, if you take an angle, say it's this amount right here, so there's your given angle theta. Coterminal to theta, coterminal to theta could be an angle that starts at the same place. We're going to end it at the same place here, but we're going to go around the circle one full time and then rotate to end up at the same spot. So this one here marked alpha. Alpha is coterminal to theta because they have the same starting point, the same ending point, but they differ in this case by a full rotation. So in other words, theta, your given angle, plus or minus 360 degrees, a full rotation. In fact, multiple full rotations will still land you back in the same spot. So if we tried another coterminal angle, perhaps I can do one here, where we start always in the positive x-axis. Let's rotate around the circle once. In fact, let's rotate around the circle to right there, and we'll end. So this one, call it angle beta, is also coterminal to the given angle here, theta, because they have the same starting point, they have the same ending point, but they differ by more than one rotation around the circle. We'll do a problem with that a little bit later. And the same is true if your measurement system is in radians, then your given angle plus or minus multiple full rotations is also called a coterminal angle. This one here that I have is not differing by multiple of rotation, but it's still coterminal because it starts and ends at the same place. It represents a larger version of the same angle. Okay, let's do an example here. Assume the following angles are in standard position. Find a positive angle less than 360 that is coterminal with the following angle. 400-degree angle. Notice that that exceeds the full rotation, so we'll subtract off a full rotation, 360 degrees. That leaves us with 40 degrees left. So a 40-degree angle is same as a 400-degree angle in the sense that they have the same starting and ending place, but they differ by how that angle was generated. Here we have a negative 135-degree angle, so that's moving in the opposite direction. So if we put here, starting right here, rotating negative 135 will bring you to there. So there's your angle there. A positive coterminal angle here, we're going to add 360 degrees, which gives us 225. So if this given angle here is theta, then instead, moving in this direction, positive rotation, that amount, call that angle beta. Beta, which is 225 degrees, is coterminal with theta, negative 135 degrees. Again, they don't have to differ exactly by a full rotation. It's a different way to be at that terminal spot, having started at the same place. This one goes in the negative direction, this one comes over in the positive direction. They start and end at the same place, therefore they are coterminal. Okay. Assume the following angles are in standard position. Find a positive angle less than 2 pi that is coterminal. So this is the same example as before, except now we're dealing with radians. We have a 13 pi over 5 angle. Okay, 13 pi over 5. Two ways to think about that. One is just simply subtract a full rotation in radians, find a common denominator, and do that arithmetic, and you get 3 pi over 5. Another way to think about it is 13 pi over 5 is 13/5 pi. Now write 13/5 as a mixed number. That's 2 3/5 pi. So that means 2 pi plus 3/5 pi. And you can see this angle of 3/5 pi differs by a full rotation. So taking out that full rotation leaves us with the coterminal angle of 3/5 pi. Suppose we have a negative pi over 15 angle. In that case, since we have a negative angle, we'll add 2 pi to it and find a common denominator, and we have 29 pi over 15. So moving in the negative direction by pi over 15 is the same as moving the longer distance, rotating the positive direction by 29 pi over 15. So those two angles are coterminal. Length of a circular arc. Let r be the radius of a circle, theta, the non-negative radian measure of the central angle. The length of the arc intercepted by the central angle S is equal to r theta. Okay, so there's a relationship I mentioned a little bit earlier on. Let's see what we can do with that. In applications in engineering and physics, they often deal with linear and angular speed. If a point is in motion on a circle of radius r through an angle of theta measured in radians in time t, then its linear speed, denoted by v, equals s over t. So this is sort of saying that velocity is distance divided by time, and the distance is s, the arc length, the distance the object moves around the circle, divided by time. So this is a different expression to say velocity is change in distance over change in time. We can then give its angular speed, denoted by the letter omega, to be theta divided by t. Now, we'll come down here. Linear speed in terms of angular speed. This is going to put two equations together. It says the linear speed v of a point, a distance r from the center of rotation, is given by v equals rw, or r omega, where omega is the angular speed in radians per unit of time. Okay, now why is that true? Well, from up above here, v equals s divided by t. So we'll write down v is s divided by t. But we know s is r times theta. So we can, here. So s is r times theta. So we'll rewrite v to be r times theta over t. And we can regroup this a little bit. R times theta over t. But theta over t, look back up here, theta over t is given by omega. So then this is r times omega. So v equals r omega. And that's where the relationship here has come from. And that's the conclusion of 5.1.